ngayon about slope stability naman tayo. Okay, so last meeting, we discussed about subsurface exploration, no? Tsaka nagbigay pa ako ng example last time through which yung kanyang mga readings after ay pinagbigyan ko kayo ng assignment through which hanapin nyo yung conclusion and of course recommendation. So what happened before was dahil nga no, yung soil strata natin mostly composing of clayey. Tapos kung titingnan natin yung moisture content, halos 100%, no? So nangyayari dun, if a clay soil is submerged in water, hindi ba hindi maganda yun kasi clay has the tendency to swell, di ba? Kaya hindi siya mainam na gamitin as foundation kasi pag nag-expand yun and nawala na yung moisture niya, nag-contract naman or nag-shrink, di ba? Ang mangyayari is magkakaroon tayo ng voids beneath, tapos baka mag-fail yung structure sa taas. So, yun yung isa sa mga pwedeng recommendation, conclusion dun. And as a recommendation, hukayin na lang ng mabuti, no? At gumamit ng piles hanggang dun sa pinaka-hard rock sa ilalim for the footing ng ating bridge. So, yun lang naman yung na-discuss last meeting. So, dito, pag-usapan naman natin bagong topic, slope stability tayo. Okay? So, bago tayo pumuntang slope stability, intindihin muna natin ano nga ba ang isang slope. So, as we all know, kapag ang slope ay present, yan ay dapat may rise at may run. So, magkakaroon ng angle between that certain vertical distance and horizontal distance. And of course, with that slope, kung iisipin natin, kung ikaw bilang person maglalakad ka sa slope na yun, medyo may hirapan ka. It's just like you going up on the flight of stairs, di ba? There are needed forces for you to go up on a certain distance kapag dadaan ka dun. And when slope stability is being discussed, isipin natin yung strength ng slope na yun para hindi siya mag-flow down. Okay? So slope stability is analyzing if the slope is safe enough. No? Yung soil natin is safe enough para hindi siya matulad sa picture na nakikita nyo ngayon. So that is one slope failure kasi. Okay? So hindi kinaya ng lupa yung bigat ng mga nasa taas kaya nangyari yan. Okay? So a slope is said to be stable if it meets the prescribed need for a fixed period of time. At kailangan nga natin ng suitable safety factor, which is pag-uusapan natin as we go along this topic. So what are the aims of the slope stability analysis? To understand the development and form of natural slopes and processes responsible for different natural features. That's the first one. The second is to assess the stability of slopes under short term. Usually, ang short term is after, no? During or just after the construction. And long-term conditions, yun naman yung matagal na time after na mismo ng construction. To assess the possibility of landslides involving natural or existing engineered slopes. So mamaya pag-usapan natin yung difference ng natural and engineered slope. No? To analyze landslides and to understand failure mechanisms and the influence of environmental factors to the slopes. To enable the redesign of failed slope and the planning and design of preventive and remedial measures if necessary. And then lastly, to study the effect of seismic loadings on slopes and embankments. So what is the overview? Slope stability analysis is used in a wide variety of geotechnical engineering problems, including but not limited to the following. So the first one would be determination of stable cut and fill slopes, assessment of overall stability of retaining walls, including global and compound stability. Includes permanent systems and temporary shoring systems, if you are to put them. Assessment of overall stability of shallow and deep foundations for structures located on slopes or over potentially unstable soils, including the determination of lateral forces applied to foundations and walls due to potentially unstable slopes. Stability assessment of landslides. So here we have mechanisms of failure and determination of design properties through back analysis and design of mitigations techniques to improve stability. And lastly, evaluation of instability due to liquefaction. So what are the different types of slope based on the method of construction? So dito papasok ang natural slope and man-made or engineered slope. So tingin ko self-explanatory naman to. So natural slopes are those what we see around us untouched by human beings, while the engineered slope are the ones being computed and made it so by people. How about the type of slope due to extents? So we have infinite slope and finite slope. Self-explanatory to, through which infinite slopes are those larger amounts, di ba? Larger amounts of distances of slope, while finite slope is near amounts. Tipong kaya lang i-comprehend. So usually, finite slopes are those on slopes and embankments and earth dams. So what are the different classifications of slope failures? So what can happen that would be detrimental to human beings when it comes to slope failures? First one would be the fall. So this is the detachment of soil and or rock fragments that fall down on a certain slope due to the gravity of the earth and of course instability of our rocks and or soils. We have the second one, topple, a forward rotation of soil and or rock mass about an axis below the center of gravity of mass being displaced. As you can see in front of you, since there are no soils that would support the downward portion of this, then possibility is due to moment, this will topple along, just like what you see in the picture. The third one, and the most common, that would be the slide. That would be the downward movement of soil mass on a certain surface. And this is most likely the ones that we will try to analyze as we go along our topic. Next is spread, the fourth one. A form of slide by translation. It occurs by sudden movement of water-bearing seams of sands or silts overlain by clays or loaded by fields. Just like what you see in front of you. And lastly, flow. This is a downward movement of soil mass similar to viscous fluid, which means that it's mostly moisturized type of soil. So what are the different causes of failure of slopes? First, gravitational force. Second, force due to seepage water. Third, erosion of surface of slopes due to flowing water. Fourth, the sudden lowering of water adjacent to a slope. And lastly, forces due to earthquake. So, let's talk about the factor of safety, which represents the stability of slope. Means that the higher the number of the factor of safety is, the more stable the slope is. And it would be usable for people or safe for the people to live with or around it. So the factor of safety with respect to strength is the ratio between the average shear strength of the soil and the average shear strength developed along the potential failure surface. So para makuha natin ang factor of safety, we need to get the ratio between the strength of the soil, or let's just say the capacity strength of the soil with respect to the applied stress in terms of shear on that particular soil. Okay? The higher the number of factor of safety is, the stronger it is. Which only means that the capacity should be larger compared to the applied stress. And in this case, the shear strength of the soil is of cohesion of soil. Okay? This is the actual cohesion of the soil property plus sigma times tangent of the angle of internal friction of the soil. While here, CD or C prime D is the actual cohesion happening applied, and this would be the angle of internal friction applied on our surface or plane of failure. We can relate this by applying now the factor of safety against cohesion to be the cohesion of the soil or the capacity cohesion of the soil over the applied cohesion. And of course, the same is true with the angle of internal friction. So the factor of safety due to friction can be with tangent of our angle of internal friction, which is the property of the soil, and this one would be the applied angle of internal friction on the soil. So lahat ng may sub D dito, that is applied value. At yung nakuha natin to laboratory tests, the properties of the soil, ay eto, yung walang D, no? Yung cohesion and this angle of internal friction. And so we can write that the factor of safety due to strength, or we could say that it's the factor of safety due to sliding, would be equal to the factor of safety due to cohesion and also equal to the factor of safety due to friction. We can write this. So now, the factor of safety, if it's less than 1, then it's a failure, which means that the applied amount of shear stress is greater than the capacity of the soil. Then, of course, the soil will fail. If the factor of safety is equal to 1, that's when it's critical. It's the borderline through which you will know whether it's going to be stable or not. So a little bit of force being applied to it would mean a failure. That's why it's called the verge of failure. Okay? So as much as possible, when we try to design our slopes, it should not be equal to 1. So the typical design we should use for a certain soil or a slope stability should have a factor of safety of 1.5 and higher. And of course, greater than 1 factor of safety should be a stable slope. So first among the two, we will try to analyze the stability of an infinite slope. So again, the analysis of this would be that the factor of safety is the capacity of the soil versus or over the applied stress or shear stress on the soil. So assuming that the pore water is not present or zero, we'll evaluate the factor of safety against sliding here. So the shear strength of soil may be given as tau F, or the shear strength of the soil, will be equal to the cohesion of the soil plus sigma prime tangent phi prime. Okay? So let us consider a slope element A, B, C, D, which has a unit length perpendicular to the plane of the section as shown. The forces F acting here are equal and opposite, so we can ignore this value. Now, going for the weight of the soil, we can compute that using our unit weight multiplied by the volume of the soil. And after that, we can compute the normal stress at the base. So the normal stress sigma prime will be equal to this NA over the area of the base. So NA over the area of the base is the same as gamma times H times L cosine beta due to the angle of the soil. And now the area of the base is used as L cosine beta. Take note, the area is considering 1 meter strip of width. Not being placed here, but it's being used. So now, the normal stress at the base is equal to gamma times H times cosine beta squared. That is for the normal stress. Now, computing naman yung shear stress at the base. So, the shear stress, we need the shear force. So, using this TA, shear force here, divided by the area of the base, it should look like this. For the normal stress, we use cosine of beta. For the shear stress, we will use the other one. Okay, simplifying our equation, the shear stress would now be equal to gamma h cosine beta sine beta. Substituting the normal stress on the equation for the actual, shear stress, it would look like this. Then substituting the shear stress at the equation here, it would look like this. Kasi nga, di ba, applied po yung pinag-uusapan natin, kaya sa applied equation din natin nilagay. So adjusting the equation, we can now get this. And we can remember that tangent phi prime, which is the applied one, will be equal to the actual tangent phi prime over the factor of safety. And of course, the applied cohesion is also equal to the true cohesion of the soil over the factor of safety. Substituting this with the values above, you can now get this equation. Then, simplifying it more, we can now get the equation of the infinite slope. So this is only true for non-seepage and non-granular soil. Okay? So this only applies for those soils which has cohesion or cohesive ones. Because granular soils are those cohesionless soils, which means that the cohesion is zero. So what would happen if we are to use this formula for those soils that are granular in nature? So if the cohesion is zero, then the factor of safety is more reliant on the friction factor and the angle of the soil. It's just that the angle of the soil should be lesser than phi prime. Okay? So this equation can also be used on sandy soils, which has no cohesion. Yun nga lang, hindi na natin magagamit ng umpisa kasi magzi-zero yung cohesion niya. Okay? So this is for non-seepage type of infinite slope. So for a seepage or the availability of seepage or a steady seepage on the slope, the equation should look like this. So the gamma below would be changed to gamma saturated, and the gamma here on this right side will be added for gamma buoyant. And we could remember that gamma buoyant is the same as gamma saturated minus the gamma of water. And this gamma sat is added here below. So that is with the steady seepage on the soil, which means that the water table is not receding or getting above. So as an example, for the infinite slope shown, considering no seepage is present, determine first the factor of safety against sliding along the soil-rock interface, and B, the height h that will provide a factor of safety of 2 against the soil and the rock. So here we have the properties of soil, gamma as 15.72 kilonewtons per cubic meter. The cohesion of the soil is 9.58 kilopascals, and the angle of internal friction of the soil is 15 degrees. So this is considering no seepage. The height of the soil is 2.44 meters. And below the soil is a rock surface. So for the solution, for the factor of safety against sliding, you can just put all the values of given on the equation provided. So here, cohesion is present, gamma is given, the height of the soil is given, the angle of the soil is provided, the angle of internal friction is provided. So, you can just put the values there. You can now get the factor of safety as 1.23. We can still say that the soil-rock interface is safe. Then, for the second one, the height h that will provide the factor of safety of 2. So, instead of the factor of safety missing, it would be the height which is missing. So, substituting 2 to the factor of safety equation and making our height be the variable. Using this equation and calculator shift solve, we can now get the height as 1.12 meters. So at the height of 1.12, the factor of safety will be 2. So ganun lang kadali ito. So going towards ganun na tayo, next topic. A while ago, we're talking about infinite slope. Now, let's talk about the finite one. So how can we determine whether a slope should be solved with infinite or it should be for finite? So if you are to get the critical height, if the critical height of the slope is the same or near the height actual of the slope, then you are to use finite. If you are to solve the critical height and found out that the critical height of the slope is too small compared to the actual height of the slope, then you can use infinite slope analysis. So, the method will be reliant on the critical height. So, for simplicity in this scenario, let's analyze the stability of finite slope using homogeneous soil, which means that the soil is the same all throughout. Okay? So evidences show that slope failures usually occur on curved surface. In actual, hindi naman siya mostly hindi naman siya yung failure na nag-slide down na straight, linear yung failure. No. That's rare cases. Most of the time, actual ay curved dapat yung surface. So pag-uusapan natin yun. So for finite slope, paano nga ba natin siya sinasolve? So before in our undergraduate, we learned about Coleman's method, through which we assume that the failure of the slope occurs on a plane, linear. Ganito, linear lang. The shearing stress here tends to slip this soil above to go downward. Okay? So here, we will analyze the shear stress acting on the soil above and the soil below. Pero using the formula naman, no, we can come up with eto na lang. I haven't shown you the equation or the derivation for this one, pero halos similar lang siya dun sa kanina, sa infinite slope. So dito sa finite slope, usually we encounter critical height na kasi. Pero, okay if we're using critical height here as the basis for our height, for us to get yung height niya na critical, then the value of cohesion should be the true value ng cohesion. Yung value ng ating angle of internal friction ay kung ano yung binigay na property ng soil natin. Why? Because in finite slope, sabi nga, di ba, you decide to go for finite slope analysis when the critical height is near to the total height or the actual height of the slope. Kung hindi sila parehas, sobrang liit lang ng critical height kumpara sa actual height ng slope, mag-infinite slope ka na lang. But in this case, we're thinking that, or we found out that the critical height is near the actual height of the slope, then let's go for finite analysis. So kung hindi critical to, if there's a possibility that you will try to solve for a non-critical height, then this cohesion will be changed to applied cohesion. Even this angle of internal friction, it will be changed into applied angle of internal friction. So mapapalitan to ng C prime D. Ito naman, Phi prime D. If the height is not critical. Of course, we have here stability number. This is a value used by our researchers who created graphs for us to better solve these problems in the future. So they created a relationship between this for them to use it in their experiments. So that later on, we can just use their graphs to solve even the most tedious ones, infinite slopes. So example, a cut is to be made in a soil having a gamma of 16.5 kilonewtons per cubic meter. It has a cohesion of 28.75 kilopascals and an angle of internal friction of 15 degrees. The side of the cut slope will make an angle of 45 degrees with the horizontal. What should be the depth of the cut slope that will have a factor of safety of 3? So dito makikita natin that the factor of safety is not equal to 1. Which means that the height is not critical. But we need to use the finite slope equation. So, ibig sabihin, the equation will not make us use the cohesion of the soil, but rather, we should use the applied cohesion. Take note, the factor of safety is 3, and we can use the earlier equations we had before. That the factor of safety is equal to the cohesion capacity of the soil divided by the applied cohesion. Manipulating the equations, it should look like this. So this is the cohesion of the soil divided by the factor of safety. Then the applied cohesion on the plane surface is now 9.58 kilopascals. Then the same is done to the angle of internal friction. And we will have now the angle of internal friction applied on the plane surface equal to 5.1 degrees. Then using these two values, we can now get the height needed or the depth needed for the cut slope. Take note, this is not the critical height because we did not use the factor of safety equal to 1. So substituting all the values here, we can get that the height or the depth needed for the cut slope is equal to 7.03 meters. That is for finite slope, Coleman's method for plane failure.